So, without further ado, let's continue with Mykhailo and his talk about how they are taming the complexities in Ackee. Thank you.
Okay. Hello, everyone. My name is Mykhailo, and I work as Android developer at Ackee. And today I would like to show you how to tame complexities using delegation. As a disclaimer, I would like to say that while this talk is based on Kotlin and Android, because that's what I mostly do, but it's really language agnostic. So the things I'm going to be talking about can be applied to any language that has some kind of reactive streams. So in Kotlin, we call those flows. But if you're using Java, you have the RxJava to help you. And if you're using Swift, you've got the combine. And the concepts and approaches from this talk apply to you as well. So to start, let me clarify what I mean when I say complexities. Imagine that we are implementing a video streaming application. And to start, we'll have just a basic video player with nothing else. It's very simple, it just plays videos, but let's be honest, it's not really useful in this state. So let's add some kind of overlay for controlling the video. So that's already much better because our users know what they're actually watching because there is a title there to help them. And they can also play or pause the video. And there is also a sig bar below, so they can sig in the video. Okay, but then the product team comes to you and they tell you that users really like watching TV shows, but they don't like watching the intro that every episode has in the beginning of the episode. So they ask you to add the skip intro button. Okay, let's put it there. But then the product team comes back again and they say that they would like to improve the user retention and that they would also like to keep users in the player for a longer time. So we need to introduce some kind of autoplay feature so that when user is close to finishing the current episode or movie, we suggest to them the next episode or the next movie that they can watch. Okay, let's say we somehow add that to our player, but then the product team is back again. And this time we need to show the age rating for the movie at some points in the video. And also sometimes we need to show content tags, which are, like violence, references to drugs. You need to show those things sometimes in the video. And I think you already see where this is going, because this was only a small part of the features that we need to implement in the player. There's actually a lot more. There are like UX features, there are a lot of analytical stuff. And how do we handle all of this? Well, to begin, let's talk about architectures a little bit. So on Android, we commonly use MVVM, and same applies to iOS. I'm guessing most of you would know what MVVM is, but if not, I'll just go through it briefly. It stands for model view model. We have the view model where we store the state, and the view is observing that view model and is reacting to changes. And the view is also able to call some kind of actions on the view model, and then the view model updates its internal state, and the view gets the new state because it's observing it. On Android, the view is typically written in Compose, and because of how Compose works, the best practice is to expose a single observable object from the view model. And this might not be the case for other platforms like iOS, but in this talk it doesn't really matter, and what I say next still applies. So this is what the screen state can typically look like. This is just a simple example where we have a title and some kind of items that we want to show on the screen. So now let's try to model our player state in a similar way. So we start by adding fields from the overlay. We've got there the title, which we'll show to the user. We also have the flag if the video is playing to show correctly the play or pause button. We have some stuff for the sig bar like current progress and total duration. And now let's add fields for the skip intro feature. So we need to show or hide it correctly at the correct points in the video. We can also put it to correct position on the screen because it can be on the left or on the right, depending on some conditions. And then we also right away add the data for the autoplay feature. So we also have, if it's visible or not, the title, the options that user can select, and the countdown until the autoplay will get dismissed automatically. And we still need to add the age rating, so let's throw that in as well. And this is still just a small set of features, and you can already see that the object is getting really, really huge. And on top of that, somewhere in that view model, we'll actually need to create this huge object. So there will be a very long function which will be creating this. And also the view model will need to handle all the actions that user can take on the screen. And there are like a lot of those. So what we are getting is a really bloated view model, which will easily have like over 1,000 lines of code. And it will be really hard to extend, because every time you'll want to add something to it, you'll have to come back to this terrible class, which no one really wants to see anymore, which has like 1,000 lines of code. And don't even ask me about testing this thing, because it's really not going to be pretty. So what do we do? Is there some smarter way to do it, which will be easy to test, maintain, and extend with more features? Well, sure, that's why I'm here today giving this talk. And the answer to this problem is some smarter architecture using delegates. But until we get there, there are still a few steps that we need to take. And the first one would be to get rid of that huge state object. And we can do that using state decomposition. To decompose a state, we need to first identify the independent feature inside of our player in our case, and identify the substates for each of those features. Then we take those like substates and create a separate class for each of them. And then we create the final screen state by combining those smaller substates using nesting. I'll show you an example and it will be clear after that. So let's take another look at our player. If you think about it really carefully, then you will see that the overlay is actually independent and we can handle it like completely separately from other features. And we can model it something like this. This is here Kotlin's SILT interface. This is equivalent to like enum in Swift. So we model it in a way that it can be either hidden or visible. And if it's visible, we pass the data that we need to show to the user. Again, like title, if it's playing, and some stuff for the sigbar. And another independent part would be that skip intro feature, which we can model in a very similar way. It can also be hidden or visible. And if it's visible, we pass there where to show this thing on the screen. And we keep doing the same thing for other features like autoplay, age rating, and others that we might have. And we end up with a final screen state that looks something like this. And this is already much nicer than before, right? And now that we have our state class sorted out, we need to talk about different approaches of creating the state and later updating it. The classic non-reactive approach would be to have the state stored in some variable or stream as a single thing. And when we want to update it, we would take it out, change some fields inside of it, and then emit the new state. And in Kotlin, it would look something like this. Here we have a function onPause, so it's reacting to user pressing the pause button. And we assume that the screen state stores the current screen state, and this .value call just gives us access to the value in the stream. And here, since user wants to pause the player, we just update the screen by copying the old value but setting the isPlaying flag to true. Okay, but this assumes flat structure for the screen state, and we've already seen that it's not really the best thing to do. So for us, it would look more like this. And this is already not very nice. And this approach is pretty hard to write when you're using nested states. And in my opinion, it doesn't even make much sense, because why would you need to access the whole screen state and mutate it in some strange ways maybe, when you just wanted to change a single independent thing on the screen? And that's where the reactive way comes in to save us. So instead of having a complete state stored somewhere, we instead need to find some, let's say, core states, which are just the smallest state variables that you've got on the screen and which you can use to later combine them into everything else you've got on the screen. Let me show you an example. We have our video overlay. And if we think about it, actually everything that we need is the metadata of the video, the current progress, and whether the video is playing. So from the metadata, we can get the title and the duration. The position is something we need to keep updating, and whether it's playing as well. And everything else can be just created by combining those three things. And the greatest thing about it is that now to update the state, you just update the appropriate state variable, and that's it. And the combination logic then takes care of the rest. And the combination logic might look something like this. This is just a very simple example, but it can also be much more complex. You can use everything that reactive streams offer, like filters, maps, transforms, whatever you need. And why I also like the reactive approach is that when you later look at this class, you see exactly what the screen state consists of, and you see exactly how the final thing is created, which is really nice. Let's now apply this approach to our player and see where we get from there. On the screen, you can see a few of our core states on top. I didn't put there all of them because there isn't space for that. So we got the metadata and whether your video is playing for the overlay. And on the right, we've got the position for skip intro and our position in the video. And we can use those and combine them into the full video overlay state and the skip intro state, which we can then use to combine into the final screen state. And then when the user performs some kind of action and we want to update the state, we simply change one of the core states on top, and then the change will automatically get propagated to the overlay state level and then to the final screen state. And that's pretty nice, right? And yeah, if you look at this diagram really carefully, you'll see that there are actually two completely independent parts there for the overlay and for the skip intro. And what if we take those parts and actually put them to some kind of black boxes, let's say, and then we'll delegate all the logic related to those features to those black boxes. Well, that's exactly our goal today, so let's see how those delegates would look like in more detail. As I've already said, a delegate is basically a black box that handles some feature. It has separate interface for actions, that's how it gets its input, and it produces a single state as an output. To show you an example, this is how the actions for the video overlay might look like. I've listed only a few of those. There is on play, on pause to react to users' actions on that button, and also on screen tap. This is to show the overlay or hide it when user presses the screen. And this would be the body of this delegate. There would also be some kind of reactive internal screen state, which I didn't put there because there wasn't space for that. There is also implementation of those actions where you would change the states in the way that you need. And we also have the video overlay state, which is the output of this delegate. And now we get to a really, really interesting part, and this is our view model. So the view model should have its own actions interface, which just inherits from all sub-interfaces for actions, from basically all interfaces of those delegates. As you see on the screen, we got player actions, which inherits from video overlay actions, skip intro. There would also be the autoplay, age rating, and so on. And this way, this player actions interface will have all the methods from the screen. And then coming to the body of the view model, we can see some Kotlin magic in action here. And by magic, I mean the by keyword. Let me explain. So here we inject our delegates to the constructor, and we let our view model implement the player actions, so it's top-level interface. But we also let it implement each of the sub-interfaces, each interface of the delegates, And we delegate its implementation to the delegate which we've injected in the constructor. And then we create the screen state by combining the like substates from the delegate. And this is like everything. I haven't really skipped or shortened anything in here. This is everything that we need. And we are just delegating all the logic to other classes. So let's summarize what we've achieved here by this architecture. We've got a really small and concise view model, which only coordinates the delegates and isn't really adding any more logic on top of that. It is really easy to extend with more features, because if you need to add something else, you just create a new delegate, you create a new interface, and you somehow add it to the final screen state. It's highly testable, since you can test each of the delegates separately. And as a bonus, the delegates can actually be polymorphic. And what I mean is you can create an interface for some delegate and put there different implementations. And we are actually using that for the player overlay, because when we have the live stream and non-live stream, they have pretty different logic for how you display the overlay. So we are doing that with polymorphic delegates, but this is out of scope of today's talk because we are running out of time. And that'll be all from me today. I highly recommend you to try out this architecture on your projects, and thank you for your attention.
So, any questions? Really? Ah, Radek.
So this looks like a well thought through architecture, but it looks like there was a bumpy road to it. How many iterations did you have to go through to like end up with this architecture that you are happy with? It looks like there was a lot of lessons that we have learned, and I would like to learn how did you get there. Thank you.
Yeah, thank you for the question. This is actually a very simplified version of what we are really doing. It's like we are using even more layers of those delegates, and it's more complex than that. And unfortunately, I didn't have the time to show all the solutions for the harder problems that we faced. But I would say this is probably the first iteration of this thing, actually, and it's working pretty well. Because, yeah, we face some issues, but there is always a way to resolve them, and it still looks pretty good. Because we are doing like a huge player based on this with like million of features, and so far it's holding pretty well.
Anyone? If no, really? So that's it for YouTube stream, because the last talk, there will be some nasty details, I guess, and it cannot be streamed online. So it's good for you that you appeared here today. I've seen that few guys are online, but they aren't asking the questions. So we will continue offline without YouTube, and hopefully you will join in person next time. And let's continue at 8.